Welcome, everyone. Thank you for signing on to the HPL seminar today. Today, we'll be hearing from Khassetara. Arash is currently a PhD student advised by Dr. Brent Edwards, and he plans to finish his PhD within the next month. Prior to his PhD, Arash completed his bachelor's and master's in mechanical engineering in Iran at the University of Tabriz. There, he specialized in solid and applied design and researched the control of car suspension systems using a vibration model, and also a vibration analysis of human soft tissues during fatigued running. Arash's current research interests include graded running, neuromuscular fatigue, musculoskeletal modeling, and finite element analyses. A fun fact about Arash is he is the youngest in his family. When he was a child, his siblings loved to play a game with him where they would tell him the name of a country and he had to say the capital city. As a result, by the time he was 6, he memorized all the countries' names and capitals, but at that time he couldn't even read or write. If Arash hadn't gone into engineering, he probably would have ended up being somewhere in the geography field. So as a reminder, I will first turn it over to Arash for his presentation, and then we will have a question and answer period to follow. And at that time, I'll remind everyone how to submit a question. Thank you, Arash, and you can start screen sharing whenever you're ready.
Okay, can everyone see my screen?
Yes, we do.
Perfect. Okay, tibial and fibular stress fractures are common overuse injuries, accounting for 3 to 20% of running-related injuries. The rate of bone stress injuries has been estimated to be 8 to 18 injuries per every 1,000 hours of running. In United States alone in 2019, 18 million people were engaged in some sort of running activity. Considering that large number, then these injuries would translate to a large number of injuries per year. By the way, this is a photo from the Great North Run, the last mile. I'm pretty sure that you recognize all of these 3 distance running legends. All of these 3 runners had some sort of running related injuries throughout their career. For example, Kenenisa Bekele is quite known for multiple stress fractures. In fact, he's coming back from an injury that costed him a gold medal. And then here, Mo Farah, the guy at the back, recently got a stress fracture in his leg that stopped him from competing Chicago Marathon this year. So stress fractures are common and occurring, and they act as barriers to achieve performance or health goals of running. It is hypothesized that the stress fractures are biomechanical events resulting from mechanical fatigue. So we have some loads that is applied to a tissue with material properties and geometry and causes stress and strain in that tissue. And then that would cause damage formation. And if the loading is repetitive, this damage would accumulate. And when the total damage becomes larger than a certain amount of damage, then an injury would occur. And of course, there is a role of remodeling, adaptation, and damage removal. But the important thing is that the mechanical loading is the initiator of this phenomenon. when we talk about mechanical fatigue phenomenon, maybe easiest is to show the fatigue life or curve or ascent curve. The ascent curve typically illustrates the magnitude of cyclic loading stress in y-axis and cycles to failure in x-axis. And it can be nicely represented with this power law relationship. Notice that the x-axis is in logarithmic scale. So a small change in stress level or a loading magnitude would cause a dramatic change in cycles to failure. For example, if we reduce the stress by 10% from sigma 1 to sigma 2, then it would correspond to 10-fold increase in fatigue life, which emphasizes the importance of a loading magnitude. And if we extrapolate this graph at some point at the stress levels below 20 megapascals or around 2000 microstrain, the specimen would survive for a few million cycles or sometimes indefinitely, which again emphasizes the importance of loading magnitude. There are different ways in biomechanics to measure or estimate tibial stresses or strain. One of these methods that have been used is to attach a strain gauge at a certain accessible area of the bone. For example, in this picture, and at the anterior medial tibial midshaft, and then have the participant perform a bunch of activities, running, walking, so on. And then we can get this nice time history of the strains within the tissue. But the problem with this method is that it is localized to a certain region of the bone, which is accessible. And it doesn't give information about the other aspects of the bone. On the other hand, attaching and detaching the strain gauges requires surgery, which further complicates the data collection, and a large-scale study is highly unlikely to happen in this case. Another method to estimate the tibial strains or tibial stresses is to basically use beam theory by modeling the tibia cross-section as a hollow ellipse, for example, here in 1/3 distal end of the tibia. And by accounting for contact forces and muscle forces and equilibrium, we can calculate the stresses within this region. And we can get the time history like this. But the problem with this method is its basic assumption that tibia is a slender beam, which may not necessarily be the case. Another method to overcome some of these shortcomings is to use finite element analysis. In this case, by considering the muscle forces and contact forces, and by applying appropriate boundary conditions and so on, we can calculate the stresses and strains within the entire region of the tibia. A number of studies have looked at the tibial strains during running by using strain gauges. For example, Burr and colleague in 1996 reported a maximum compressive strain of around 1200 microstrain and a maximum tensile strain of 700 microstrain in a bunch of vigorous activities like lever running, uphill running, downhill running, and so on. Milgram and colleagues a few years later, using similar method, they reported around 1700 microstrain in maximum compressive strain and a maximum tensile strain of around 1300 microstrain. And they use these a bunch of different activities from running, biking, sprinting, leg press, and so on. And Milgram and colleagues in 2003, using quite similar method, they reported maximum compressive strain of 2400 microstrain and maximum tensile strain of 1200 microstrain. We previously mentioned that the cortical bone will survive a couple million cycles before failure in these strain ranges. So by that logic, the stress fracture should not happen in real life. But we know that stress fractures happen way before even 100,000 cycles of loading. Therefore, there is a clear discrepancy between the strain gauge observations and real life. There are a number of explanations for this discrepancy, one of which is the effect of neuromuscular fatigue. According to Powell's hypothesis, the lower extremity muscles produce protective forces against bending of long bones. In case of femur, for example, it makes perfect sense. When we apply the contact forces, hip contact force at the femoral head, this force tends to bend the femur medially, while the forces, for example, from the gluteus muscles try to oppose this bending. So if there is somehow a decrease in muscle forces, let's say by neuromuscular fatigue, then the strain should increase within the long bone. A few studies have looked at tibial strains in presence of neuromuscular fatigue and hypothesized that the muscle fatigue would cause increased tibial strain during running. But the results are inconsistent. For example, Milgram and colleagues, by using strain gauges, reported 29% increase in peak compressive strain after a 30-kilometer march. Similarly, Rice and colleagues, by applying beam theory, they reported 15% increase in peak stresses after a 40-minute treadmill run. On the other hand, Fury and colleagues, using strain gauges, they reported no change in 20-minute treadmill run of canines. Or similarly, Rice and colleagues, by using beam theory, they reported also no changes after a 7-minute calf raise exercise. As we mentioned before, the problem with these strain gauge or localized beam theory studies is that they are localized to a certain region of the tibia and they don't give information about other aspects. And as we explained, the finite element analysis might be better in explaining showing the strains within the whole bone. The only finite element analysis, that we are aware of is by Burnett and colleagues in 2017, and they reported 5% decrease after a 112-minute treadmill run. By that, the purpose of our study was to determine changes in tibial strain during a prolonged downhill run using finite element analysis. As I mentioned before, the Powell's theory makes perfect sense in terms of femur, but in terms of tibia, the contact forces, for example, the ankle contact force tries to bend the tibia posteriorly. At the same time, the forces from large plantar flexor muscles try to bend the tibia in the same direction. So if there is a reduction in muscle forces by neuromuscular fatigue, then we should expect a decrease in tibial strains. By that, we hypothesized that the tibial strains would reduce throughout the prolonged downhill run. To test our hypothesis, we recruited 12 physically active males, and they performed a 30-minute downhill running bout on an instrumented treadmill at a constant speed of 2.8 meters per second and the constant grade of negative 11.3 degrees. For reference, this grade would be like running down the 29th street on the Hospital Hill, or a bit less steep than the Nose Hill Park. We measured ground reaction force and 3D motion data at minutes 1, 15, and 29. Here we will call T1, T15, and T29. We specifically chose prolonged downhill running as fatiguing protocol because our previous study from the same database showed significant neuromuscular fatigue after downhill run, which manifested in 16% reduction in knee extensor maximum voluntary contraction force. In the same study, we also indirectly measured the muscle damage, and we found up to 2.5-fold increase in serum creatine kinase activity, which shows that the protocol was fatiguing enough. Similar protocols have been used in the literature before. For example, a 34-minute trail downhill run caused a significant reduction in knee extensors and plantar flexor MVC. And therefore, we believe that this protocol was appropriate to investigate the effect of neuromuscular fatigue. As the title of the talk suggests, we used a finite element analysis in this study. There are 3 sets of data sets of data that we need to we need to create a finite element model. Joint contact and muscle forces, bone geometry and material properties, and assigning boundary conditions. And I'm gonna go ahead and talk one by one about these elements. For determining joint contact and muscle forces, we used a musculoskeletal modeling workflow. So this is a quite messy slide, so I'm gonna go step by step. The whole process is an optimization to find muscle forces by minimizing a certain objective function. First, we start with scaling a musculoskeletal model of 44 muscle tendon units. And for every 1% of stance time, we calculate muscle moment arms, and we calculate the maximum dynamic muscle forces by accounting for force velocity and force length relationship. And from the inverse dynamic, we calculate the joint torques. And here in the optimization procedure, we minimize the cost function, which is the sum of muscle stresses squared. And this cost function should be optimized in a way that the torques that the muscles produce would be the same as the joint torques from the inverse dynamics. And then the output would be the muscle forces, and the joint contact forces would be the algebraic sum of the joint reaction forces from inverse dynamic and muscle forces from musculoskeletal modeling. For determining bone geometry and material properties, we used a database of 27 CT images that we had in our lab to predict bone mineral content of the tibia based on height and weight of the participant. And our equation could predict 64% of the variation in bone mineral content. Then we determined the closest match CT based on BMC for each of our participants. This approach was verified by 4 CT images that we had from our participants in downhill running study. So we created a series of FE models by using the CT images from our participants, calling participant-specific model. And then we also created a series of FE models using the match CTs. As you can see, there are subtle differences between in geometry and material properties between the 2 models, but the overall distribution of the strains are quite the same. And at the same time, this approach, the absolute magnitudes of strains were different between the 2 approaches, but the changes in strain over time, which the one that we cared about in the study, was in strong agreement with the participant-specific model. So here we we calculated, for example, maximum principal strain or minimum principal strain from T29 to T1, the changes in these variables. And then we looked at the R squared between the two methods. The R squared is around 0.95, which is in excellent agreement. And the same scenario was for the strain volume measurements as well, with R squared of 0.7. So we talked a lot about the FE model. To reiterate, we took the height and body mass of our participants and then determined the best matched CT image based on predicted bone mineral content. And then we scaled the tibia and fibula based on participants' height. And then we assigned material properties based on CT apparent density. We considered the bone as inhomogeneous orthotropic material, where the Young's modulus is a function of the apparent density of the CT. And we assigned quadratic tetrahedral element in abacus for meshing the FE model, and with an average element size of 2 millimeter, which resulted in around 310,000 elements for tibia and 70,000 elements for the fibula. For the boundary conditions, we fixed the knee joint in 3 directions. And then we fixed the ankle joint in mediolateral and anterior posterior direction. And then the nearby elements in tibia and fibula were tied together. And we then applied the muscle forces and contact forces from the MSK modeling and the residual moments to the ankle joint. And then we used this boundary conditions because they could predict structural deformations as, for example, anterior posterior deformation of the tibia or mediolateral deformation or torsional deformation of the tibia in agreement with a bone pin study. We were interested in strains within the tibia and fibular midshaft as shown in red here. We looked at maximum principal strain and failure criterion, and we looked at 1 Mises strain, which has been used for failure criterion of ductile materials. And we also looked at pressure modified 1 Mises strain, which has been shown to be a good failure criterion for orthotropic materials. And when we look at the histogram of the strains, we were interested in 50th percentile strain based on these measurements. And we were also interested in 90th percentile strain as high strain. Also, the strain volume has been shown to better predict the fatigue failure of bone. Therefore, we defined the volume of elements with strains above 22,000 microstrain as strain volume using these 3 methods, criterion. Before I move to strain output from our FE model, I'd like to draw your attention to some of the changes in downhill running biomechanics that we observed during this study. The contact time of running increased by 25 milliseconds or 8.5% at the end of the run. The flight time reduced by 24 milliseconds or 32% at the end of the run, while the step frequency did not change, which means that the downhill running biomechanics changed significantly throughout this run. Then moving on to contact forces. Here we have an example of ankle contact forces at 3 different time points for a representative participant from T1 to T29. We can see a reduction in the magnitude of the maximum resultant force. Same story is true for knee contact forces. And when we look at our results, the resultant ankle contact force reduced by 4.5% at T29 compared to T1. And the peak resultant knee contact force reduced by 5.5% at the end of the run compared to the beginning, while the hip contact force did not change. Moving on to tibial strains, our 50th and 90th percentile maximum principal strain did not change throughout the run, while our 90th percentile von Mises strain and 90th percentile pressure modified von Mises strain reduced by around 4.5% at T15 compared to T1, but there was no difference between T29 and T1. And the strain volume measure did not change throughout the run. So all in all, we can say that there wasn't a systematic change in tibial strains throughout the run. So the reduction in peak contact forces may be due to increased contact time, which redistributed the contact forces in longer time, causing a reduction in peak magnitudes. But we also said that the contact forces went down, but the tibial strains did not change. And how it is possible, when we look at the different components of, for example, ankle contact force, we can look at the axial component, AP component, and the mediolateral component. The axial component reduced by 8% at the end of the run, but the AP component increased by 12%, and the mediolateral component did not change. So the axial component is actually contributing to compression in the tibio-fibular complex, while the AP component is contributing to the bending. So the reduction in compression and with increase in bending, they were neutralized each other, and the net effect was no change in tibial strains. There were some limitations in this study. The first limitation was the lack of CT images. So a participant-specific FE model could have better accounted for geometry and the material properties. But also we showed that for the 4 participants that we looked at, the changes in tibial strain using BMC matched model was strongly in agreement with the participant-specific model. We only recruited male participants in this study, while the epidemiological studies have shown that there's a higher rate of stress fracture among female versus male runners. And although there are some sex differences in running biomechanics, for example, in knee joint moments or patellofemoral contact forces, but the changes in, for example, patellofemoral contact joint is not different between the 2 sexes, at least based on this last study. And then the running protocol was another limitation, that the same constant speed was chosen for all participants, which may not necessarily show the same workload for all the participants, although determining a appropriate speed for downhill running is quite challenging, because downhill running performance is not limited by the VO2 max or aerobic capacity. The take-home messages of this study is that the prolonged downhill running bout caused significant changes to running biomechanics, And while resultant ankle contact forces reduced, the FE predicted strains did not change throughout the prolonged run. And we conclude that the effect of neuromuscular fatigue on tibial strains are either very small or insignificant. And the relationship between contact forces and tibial strain is complex and non-intuitive, as increase in the reduction in ankle contact force did not necessarily cause a reduction in strains. With that, I'd like to first of all thank the participants in this study, and then I'd like to specifically thank Dr. Ifaz Haider for being my FEM mentor in this specific study. And I also like to specifically thank Michael Bagley for sharing his slides with me, and also for lots of interesting discussions. And also I'd like to thank Edwards Group and my source of funding. Thank you.
Thank you, Arash. That was a great presentation, and now we'll transition to the question and answer period. At this time, I would kindly ask the audience members to turn on their camera if they're comfortable, to allow for a better discussion period. To ask your question, you can use the raise hand function on Zoom, which is located on the lower part of your screen under reactions, and I will call on individuals from there. Alternatively, if you are unable to raise your hand, you may type your question in the chat box and I will ask your question aloud. And again, I think we have plenty of time for discussion, but we'll try to wrap up by 4:15 today. And Art, would you like to start us off, please?
Sure, I guess I have two questions. One of them is just about your first diagram where you showed a force being applied on the femur, and then you pointed out how the muscle basically adds to the strain of the bone, which I completely agree with. But I was under the impression that muscles are the primary factor in bone strain no matter what, meaning that muscles produce forces that are multiple times the ground reaction force. And also the bones are generally in equilibrium. So I sort of feel like the force that you apply from the, from the other part of the hip is less important than just what the overall load is. Basically, shouldn't the overall load with muscles and everything already be an indicator that that since that things are in equilibrium, that there's a high load on the bone or high strain?
Well, the forces that are applied for the forces that are applied to the end of the bone, the contact forces, are somehow resultant of the muscle forces as well. Yes, and the whole bone should be in equilibrium. But then, if we, in case of femur, for example, when we look at the contact force, it is quite obvious that forces coming from one muscle is pulling the bone, for example, from gluteus muscle, pulling the bone in one direction, while the contact force, which is again the sum of those muscle forces coming from the in this case proximal end of the femur, also trying to bend the bone on the other direction. So if the force in one direction increases, if the muscle forces in one direction increases, and in the bending of the femur would which is caused by the contact force would reduce, then in that case it makes sense to assume that a reduction in the muscle force would cause an increase tibial strain.
I see. And my second question is related to that, which is, for decades ago, I think people have been interested in the same question. And back then they would just use, say, the ground reaction forces as the indicator of the bone strain. and then they would, I think the only information they had back then was just the joint reaction forces as computed by inverse dynamics. In other words, just the resultant forces. And so I think you have a huge advantage here because you have actual muscle geometry, and you're able to calculate loads much better than what people did back in the past from ground reaction force. So I'm just curious, are there some cases you can pinpoint where you calculated something that highlights basically the error from what people had done in the past, basically where ground reaction forces are insufficient to predict something that you observed?
Well, I can remember a study from 1970 or early 1980s that in those ages they used this basically the reaction force from the at the joint, not the contact force, but there's no like a specific model that I can say they didn't look at the whole tibia, for example. The study that I remember was just the proximal tibia. They didn't look at the whole tibia too specifically. We can compare the two studies, but definitely if you have smaller forces, I think their force was around 2,500 newtons at the knee, which is the contact forces are way higher than that. Then you would expect a higher strain in the bone.
Mm-hmm. Yeah, so I just think that you have an opportunity to highlight some errors from the past calculations because you actually do have so much more information.
Yes.
Okay, thanks.
Thank you.
I'll jump in with a question, Arash. Did you report in any of your slides the location of peak strain or stress, and did that change throughout the prolonged run?
We did not report the specific location of the peak stress. One thing that it is happening in the compression in the back of the bone, the posterior part of the tibia, but the question is, should we report the peak, the location of the peak strain or not? We could report the 90th percentile strain, that just to make sure that it is close enough at a certain location of the bone. But yeah, we haven't done it yet. We will add that to the study. Thank you.
Yeah, and the reason I'm asking is when we think about bone damage, then should I be thinking about repeated loading and the damage risk of the whole bone, or like the repeated loading and the risk of damage to each tiny element and location of the bone? Because right there's possibilities that like area of peak strain is changing loading cycle to loading cycle, right?
Mm-hmm. Well, the ex vivo studies on cortical bones, for example, shows that looking at strain volume would be a better representation of a better predictor of fatigue life of that specimen. So it would be probably better to look at the volume of elements that experiencing a certain amount of strain, rather than just looking at just one point at the bone.
Do you have a gut feeling from your data how I don't remember if you said stress or strain volume might change across your 3 time points?
We actually looked at the changes in strain volume, and they did not significantly change throughout the fatiguing run, which again explains why we concluded that the effect of neuromuscular fatigue may not necessarily be very large, or it's either very small or insignificant in tibial strains in general.
Thanks. Walter, would you like to go ahead, please?
Sure, yeah. Thanks, Arash. That was very nice. Can you explain to me why some people think that muscle fatigue would cause more strains in bone?
Well, the reason they thought that it would cause more strain in the bone is based on the argument in Powell's textbook. In that textbook, he, again, in case of femur, he didn't talk a lot about the tibia. He talked a lot about the femur specifically in that textbook. And again, the argument that I showed in the beginning, that the contact forces trying to, for the femur, contact forces trying to bend the femur medially, while at the same time the forces from gluteus muscles, for example, trying to oppose this bending. So if there's a reduction in this muscle force due to the, for example, neuromuscular fatigue, then you would expect that this opposing force would be smaller, resulting in increased strain.
But if you had a decrease in muscular force, that essentially would mean that you somehow have to change the movement, because if the movement was the same and you had the same ground reaction forces, then that would not really happen. So the idea is that with fatigue, you somehow change the movement pattern within the constraint of what you need to do. Let's say run down hills at 10 kilometers per hour. And then that has the effect that strains are increased in the bone. Do I understand that correct?
Yes. So basically, there is something is changing. For example, in terms of, in those studies, they didn't look at the movement pattern specifically. For the strain gauge studies, they were only interested in specific location and the changes in strain. And for the beam theory studies, they also didn't report much about the movement pattern. But here, for example, we showed that the contact time increased during the 30-minute run, which means that the same force is redistributed in longer time. That, yes, it would reduce the peak magnitude of that specific force.
And the flight time became shorter, which suggests that they might not have raised the center of mass as much, and therefore would not have come, like, fallen down as much as they otherwise would. Yeah. So that kind of small changes in movement will cause measurable changes in the bone strain. So you showed a series of fatigue studies that showed an increase in bone strain, and then you showed a series of studies that didn't show that. They were neutral. They said there were no change. Is there a difference between these studies?
The main thing about the strain gauge studies, these studies were either strain gauge studies or beam theory studies. And they were just looking at for beam theory study, they were only looking at a certain cross section of the tibia, for example, 1/3 distal. And for the strain gauge studies specifically, they put a strain gauge at a certain accessible area on the tibia. But that certain accessible area is actually very close to the neutral axis of bending. And therefore, the measurements are not that much reliable, I'd say. First of all, it is a single point measurement. And secondly, it is close to a neutral axis. That, first of all, it doesn't show it wouldn't be the strain that you would get there wouldn't necessarily be even closer to the peak strains. And then just changing the location of that specific strain gauge in another study might change the result, basically. But I can say from that 4 studies, the net effect was, so 2 studies increased, 2 studies no change. The net, and then 1 study decreased. The net effect would be either no change or very small changes.
I'm not sure because the slide was a bit fast, but it seemed to me that the one that didn't show change was a leg raise study, and the other one was in dogs, a 4-legged animal.
Yes.
And the 2 that showed the change were running studies in humans.
Yes, the 2 studies that showed the changes, one was 30-kilometer march, and after a 30-kilometer march, they did this running test before and after it. So it was fatiguing, and I believe that they also reported the plantar flexor reduction, the reduction in the MBC of plantar flexor group. And the same thing, yes, there are some differences between the studies. The same thing is for the 7-minute calf raise study, that although they didn't necessarily report the changes in MBC, but 7-minute calf raise is challenging enough to assume that the neuromuscular fatigue is actually happening.
I was just wondering, because you saw the difference in the 2 studies that assessed it with running, but you didn't see it in the dog, it's a 4-legged animal, and you didn't see it in the leg raises, that the very simple explanation might be that in running you measure something very different than in other conditions or in a dog.
I agree with the dog study, although they did this, it was a weird study. The dog were actually walking, almost running on their 2 legs, the hind limbs. But the front legs were somehow constrained. For the calf raise study, they looked at the strains during running, but the fatiguing protocol was a 7-minute calf raise study.
Okay, I misunderstood that then. The other thing that I was wondering is you made a big deal about the bone mineral content, and that you could explain that with the height and the weight of the people. And you gave bone mineral content in grams. So is that like the amount of bone mineral content in the tibia? Yes. And taller people and heavier people have bigger bones, and therefore they have more grams of bone mineral. Is that a simple explanation? Taller people and bigger people have more of that?
Yes, based on the equation, the taller people would have, so you have a bone mineral content would be a function of the volume of the bone, first of all, right?
Yeah.
So the taller people, or like bigger people, would have a larger bone mineral content.
Yeah, and that makes a lot of sense to me, but I'm not really sure. I couldn't really explain to me why that potentially might be important in the context of of fracture risk. There I thought the bone mineral density would be much more important, and later on when you go into that, then you actually have a bone mineral density measure, which makes sense to me. So was there a reason for doing the bone mineral content, the total content, that I might have missed in the context of injury?
Yes, I actually went very fast on that slide. I should have gone a bit slower. So for bone mineral content, so we were interested in finding out how, so we have this database of CT images, and then we have some participant that we don't have their CT images. We want to match each of these participants with one of these databases, right? So we came up with this equation for bone mineral content. And then based on that, we matched the participants from our study with that database. But bone mineral density wouldn't actually change much, especially these people are young people. So you would expect a bone mineral density around like 1.1-ish for all of them. So you wouldn't have enough scatter to try to have an equation based on bone mineral density. And that was the reason we tried to use that one. But in terms of assigning material properties, so there's been a lot of studies showing that there's a good relationship between the density of the bone and basically their mechanical properties like Young modulus.
Okay, yeah. I have a couple more questions, but I'm gonna stop here and let other people ask. Except if absolutely nobody wants to chat, then I'm happy to ask a couple more questions.
Thank you.
Art, did you have additional questions?
I know I'm all set. Thanks.
Perfect. Rob, please go ahead.
Arash, I enjoyed all of that. I'm wondering about whether bone is viscous, and I'm sort of thinking about a high impulse that might happen, that might be causing the injury. The thing that struck me was your very first slide. You said you had 8 to 18 injuries in per 1,000 hours, and it struck me as very, very high. And so I'm wondering if, from the bone point of view, is there something to do with our running that gives a sudden high impulse? And, you know, I remember Benno's work years ago. The gentlest way to run was on your toes, barefoot on grass, to give the least impulse at the joints. Is there a viscous element to bone or a flexibility issue to bone that would prevent this injury occurring? Or
there is a viscoelastic element of bone, but the rate of change, the relationship between the rate of strain and the changes in fatigue life of the bone is by a power of 0.001, which means that is very small, and it would only show itself in like a car accident.
right.
Not something like running that doesn't have enough fast like impact like effect.
I'm surprised, because if you look at, you had dogs there, if you look at wolves run 20 to 30 miles a day, up to 100 miles in a day, and they spend about a third of their day in travel. And clearly they're not suffering these sorts of injuries. So what are we doing wrong that they're doing right?
That's a good question.
4 versus 2 legs.
Well, maybe.
Well, that could be one reason. The magnitude of loading has, based on the graph that I showed, the inverse power law, the magnitude of loading is very, very much determining the fatigue behavior of the bone. So if even there's a small change in magnitude, then if you have 4 legs compared to 2 legs, then you probably would end up with a huge change in the number of cycles to failure.
What about kangaroos? I've got some just here.
Well,
I'm just wondering if there's a fundamental difference between what you're measuring in people running versus animals that have evolved to do it all the time, and whether it actually comes back to the sorts of things that Benno showed years ago with the impulses at the joint with running on toes, on grass versus running in shoes and on a different surface. I'm wondering if these injuries that you started off talking about, whether that's where the mix is.
Yeah, there's been a lot of studies talking about this loading rate. Basically, you run on your toes, then the loading rate is smaller, and then you run on your hill, the loading rate is larger, then they said that, okay, this shows that running on your toes is better. But the fact is, first of all, based on the ex vivo measure tests of the bone, the loading rate, the change in loading rate by that much would have no effect, first of all, on, like it would be very small that you can't even see. And if there is an effect, actually the increased strain rate would increase the, increase the fatigue life of the bone. And if there is any effect, the effect is very small. So I wouldn't assume that changes in loading rate based on changing in a running pattern would have any effect on fatigue or the stress fracture of the bone.
Okay, thanks, Arash.
Thank you.
Are there other questions from the audience members? Great, Walter, go ahead, please.
Sure, but anybody interrupts me if you want to ask a question. The other thing that I was wondering is, you gave these two numbers about muscle fatigue, and I didn't know if that was obtained in downhill running, and if it was obtained in downhill running, I would be really surprised. And that was, a 19% decrease in muscle strength after an activity and 26% in the plantar flexors. Was that done after downhill running fatigue?
It was after a downhill running, trail running for 34 minutes on average. But the thing was that they ran as fast as possible. Basically, it was like a time trial thing, not necessarily.
So it was a trail run. So it was up and down and up. So it was not downhill running only.
It was mostly downhill.
Okay, because I'm surprised that your calf muscles would get fatigued in downhill running. I mean, having done some downhill running, I know my knee extensors start hurting after a while, but very, very surprised that you would get more fatigue in the calf muscles in downhill running. It seems to me they don't really do anything much when you run downhill, but maybe I'm wrong.
I assume if you're running on your toes specifically, they do a lot of eccentric contraction there as well to absorb some of the loads. You can try it. You can run with your heel all the way downhill, or you can try with your toes, and they do a lot of eccentric contraction.
Well, I'm naturally a midfoot runner, and also do that when it's slightly downhill, but I know when it gets very steep, that's when I actually land on my heels. But it has to be very steep. So were your runners that you had forefoot strikers mostly then?
We had, I think we had two forefoot strikers. I haven't necessarily looked at the exact, I haven't analyzed the data that way. But based on just what I saw, we had at least two forefoot strikers. In their study, I assume, because if I'm not, again, they didn't say anything about it, but I'm assuming if you're running as fast as possible, you would go on your toes. Even if it's downhill, but again, I might be wrong.
And a very, very technical question. Can you explain, or was there a reason for your muscular force optimization why you used some of the muscle stresses to the second power? Why you used that crown, shield, and Brand to the second power equation? Was there a reason, or was that just because it's there and available and easy to do?
They actually, in that study in 1980s, 81, I guess, they showed that this optimization, this cost function, results in a reasonable time history of the forces of the muscles that are in agreement with the EMG studies, EMG measurements as well. So although the choice of cost function wouldn't necessarily change the result that much, actually my colleague Michael Bagley did some study on that as well. So it doesn't necessarily change the end result of the, if you use different cost function, it wouldn't change it by much.
I'm not sure if you would change it much if you use different cost functions, but actually Crownshield and Brand, they make an argument based on physiological considerations, and you can argue yes or no, but they actually make an argument that you should take that function to the third power. But you can actually show that for the second, third, or fifth or seventh power, the timing of the muscles would exactly stay the same. The magnitude that you predict would vary very slightly, and but the timing would actually not change. I was just wondering, because they make such a big argument about taking the muscle stress to the third power, why you decided to take the second power.
And I think the end result wouldn't again change too much if we go with 2 or 3. And actually, we have tried that one as well. But the whole point is that the forces that are predicted by this MSK modeling is quite in agreement with the EMG studies as well.
Yeah, and it has to be, because it can show that in nonlinear optimization, if you have a simple case, let's say the simplest case is a one joint muscle, and in nonlinear optimization, when of the type of the Crownshield and Brand type, if you have a torque that's agonistic to the muscle force, to the torque that the muscle will produce, that muscle will be on, it will come on. And so there's certain restrictions of that, you know, that where it really doesn't matter. And as I said, what exponent you take actually doesn't change the timing.
Yes, I agree. A linear cost function wouldn't result in the same thing that we saw.
No, linear is completely different, because in linear optimization, you only get as many non-zero forces as you have constraint equations. And like Crownshield and Brand, you know, they had 3 degrees of rotational freedom at the hip, and I think 1 at the knee and 2 at the ankles. That would be 6. So the maximum number of muscle forces they would predict in a linear optimization using a simplex algorithm would be 6. Except if you have a very funny situation where you have a constraint, a linear constraint, and your cost function is exactly parallel to it. But if it's not, then you only can predict as many non-zero forces as you have constraints in a simplex algorithm, which is what you did in high school when you solved linear optimization problems.
Yeah, I agree.
Great. I'm going to read a question from the chat, Arash. You had one subject with very high ankle contact forces. Why was that?
For that one subject, actually, the first of all, the flight time was really high for that specific subject. He was running quite differently than other participants, and the step frequency for this subject was quite low. So that is the reason for that specific participant. I think his step frequency was around like 150 or even lower than that. And yeah, that the same subject that probably was the worst case scenario for this study. I used the time history of the same subject when I was explaining here in my slides, as like the worst case scenario is that one. Yeah.
Great. Siska, please go ahead.
Hi, thanks for your talk. I just have a quick question. You said that your participants are trained males, and I was just wondering if you can define what you mean with trained, and if that differs from the populations from the other studies you discussed in the beginning. And then I was wondering as well if you think that there can be individual responses and that maybe in certain persons there would be increases, while in others there may be no changes.
For the first question, our participants were physically active males, not necessarily trained. They were trained enough to be able to do a 30-minute downhill run, but they weren't trained runners.
Okay, so you don't know how often they were actually training or running or?
We do have some data of these participants, but if you really want to know, they definitely ran above 10-15 kilometers per week to be able to do this study. But like a specific value for like VO2 max, we didn't measure that specifically to know what aerobic capacity they had. For the second question, there were individual response in the data that we saw. Some of the participants showed a large reduction in, for example, tibial strains, while some others showed no change and some others showed increase. So it is if we had a very large scale study with a large number of participants, it would be possible to group them probably.
And then just how did your population differ from the other studies that were looking at downhill running?
The other study that they mostly talked about the physiology of the downhill running, and in those studies, most of the studies, for physiology of downhill running, you would want someone who's not accustomed to downhill running. So you could see some like repeated bout effects if you're interested in that one. For those type of studies, the participants were not well trained. For some other study that you just want to look at just one bout of downhill running, you would want someone who's a trail runner specifically, so they're already accustomed, the repeated bout effect occurred, and then for those studies they would be trained runners.
Okay. Thanks.
Thank you.
I have another question, Arash. Can you talk about level and uphill running? Do you think the trends you saw would be similar?
The trend that we saw in contact forces, for example, there hasn't been any study specifically, any paper, I should say, that like journal paper that looked at the contact forces during a prolonged run, but there has been two theses that I'm aware of that they reported contact forces. One reported after 112-minute level running on treadmill, and the other reported after, if I'm not mistaken, 86 minutes level running on treadmill. And they both reported a reduction in contact force in level running. And here in downhill running, we also showed a reduction in contact force. But about the tibial strains specifically, one study showed a reduction, as I mentioned in the slides, 5% reduction, and the other one did not report any changes. And here we also did not report any changes. So if you, I think there should be more studies to actually be able to say completely with complete certainty, but the effects of neuromuscular fatigue in general on tibial strains would probably be very small or insignificant.
Are there other questions from the audience? Okay, great. Arash, thank you so much for your presentation today. And thank you to all the audience members for their questions. Next week, we will be hearing from Songwon, and her talk title is Residual Force Depression in Cardiac Myofibrils. I hope everyone has a great day, and I hope to see you all at seminar again next week.